Hello everyone, my name is Jyotika Tanabalan and my matrix number is B0822102243. Our assignment title is Digital Signal Processing Windowing Filters. So we chose rectangular windowing and also Hamming windowing. So let's go into the video where my group members will introduce themselves.
My name is Konila Chandran. My matrix number is B0822100091.
Hi, my name is Jagdishan, son of Punasekaran. My matrix number B0822102000.
Hello, my name is Sharat Kannan. My matrix number is B0822100174.
Hi, my name is Kuman Krishnan. My matrix number is B0822102202.
Spectral audio analysts analyze audio frequency for applications like speech recognition and music processing. Window functions such as the Hamming and rectangular windows are crucial for shaping signals. What is Hamming and rectangular window? The Hamming window is a small bell-shaped function used in the digital signal processing to taper signal edges, reducing spectral leakage and enhancing frequency domain clarity. It's ideal for applications like speech processing and audio analysis, balancing resolution and interference reduction. A rectangular window is a simple function that applies uniform weights to a signal segment, effectively cutting it a specific length. It's somewhat computationally efficient but lack of edge smoothing, leading to a higher spectral leakage. It's suitable for tasks prioritizing simplicity and speed. Benefits of the Hamming window: minimize spectral leakage. The Hamming window smoothness signals edges, reducing amplitude transitions and minimizing interference in the frequency domain. But better frequency resolution, it provides a balance between main loop right and a side loop suspension, making it effective for application needing clarity into frequency spectrum. The benefits of the rectangular window is the simplicity. The rectangular window applies uniform weights, making it straightforward and easy to implement. The second is complementation efficiency. It's a constant weight function, reduce less processing, making it suitable for application prioritizing speed. These are the example signal pictures. The first picture is the original signal. The second is a Hamming window signal. The third is a window wet signal. The last is a rectangular window signal.
Okay, now we see the difference between a rectangular window and also Hamming window. So the first one, we see the definition of rectangular window. A rectangular window is the simplest window function. It is constant, uniform over its duration and abruptly cut off to zero outside the window length. And also for the Hamming window, the definition is the Hamming window is a tapped window function designed to reduce the amplitude of the side lobes, thereby improving the suppression of spectral leakage. So for the rectangular window, the amplitude will be constant, and also for the Hamming window, the amplitude will be reduced at the edge. So now we see the formula for rectangular window. So the for the rectangular window is Wn equals to 1 for above than 0 and also below than n. For Hamming window, the one Wn equals to 0.54 minus 0.46 cos 2 pi n over n minus 1. So for the frequency resolution, the rectangular window provides better frequency resolution but poorer side lobe suppression. But for the Hamming window, offers moderate frequency resolution with good side lobe suppression. So for the rectangular window, the one resolution is better, and also for the Hamming window, the one is slightly worse. So then another difference is side lobe level. So for rectangular window, high side lobe levels causing significant spectral leakage, and also for the Hamming window, reduced side lobe levels minimizing spectral leakage. So then we see the main lobe width. So for rectangular window, the one narrower main lobe, making it suitable for distinguishing closely spaced frequencies. And also for the Hamming window, it's wider main lobe, reducing the ability to resolve close frequencies. So after that we can see the applications. So for applications for rectangular window is suitable when the signal of interest is well isolated in frequency, and also used for basic applications where spectral leakage is not a significant concern. And also for the Hamming window, the application is for speech processing, spectrum analysis, and also filter design.
One of the example application of rectangular window is pulse analysis in radar systems. Radar systems rely on the precise detection and analysis of electromagnetic pulses reflected from objects. The rectangular window is used in radar signal processing to analyze pulses of electromagnetic waves. The time of flight of a pulse is directly related to the target's range, so precise timing is essential. Rectangular windowing preserves sharp transitions in the pulse waveform, ensuring that no smoothing or tapering is applied to the signal. This is important for applications requiring high temporal resolution, such as detecting short-lived or fast-moving objects. Examples of real application in radars are military and aviation radar, where it is used for tracking fast-moving aircraft or missiles. Then, automotive radar, it is used for collision avoidance in autonomous vehicles. Lastly, weather radar, where it is used for analyzing short duration precipitation signals. Then, the image in the slide displays the noisy radar pulse that contains Gaussian noise that distorts the rectangular pulse shape. After applying the rectangular window, the pulse structure is preserved, focusing on the time domain features. As the next part, we get into the application of Hamming window. Audio signal processing is one of the applications of Hamming window. Audio signals are often converted from the time domain to frequency domain for tasks like speech detection or noise identification. Hamming window tapers the signal towards zero at the edges, ensuring a smooth transition at segment boundaries. This minimizes spectral leakage that leads to more accuracy of frequency domain analysis. For example, the Hamming window is used in voice recognition systems such as Siri, Alexa to pre-process speech signals, ensuring that the extracted features are accurate and free of artifact. The image in the slide above shows noisy speech signal contains noise that hides the primary frequency components. After applying the Hamming window, the signal's edges are smooth, reducing spectral leakage for better frequency domain analysis. So, we can conclude that the rectangular windowing can be used for time domain tasks. Meanwhile, Hamming windowing can be used for frequency domain tasks. The windowing functions are selected based on the specific requirements of the application. So, before this, we have seen the explanation for real applications of rectangular and also Hamming windowing. So, now let's see the simulations that we have been done for both the windowings. So this first slide shows the simulation that we have been done for rectangular windowing, which is radar pulse analysis using rectangular window. So it shows the process of designing a filter using a rectangular window and applying it to a noisy radar pulse signal. In this case, the convolution operation is applied to the noisy radar signal using the filter coefficients. And also, the convolution will attenuate or remove high frequency components such as noise based on the low pass filter designs, because we have used low pass filter design in this coding. For the results, as you can see, there are two plots, which are top plot and also bottom plot. The top plot represents noisy radar pulse signal, which is the original signal before filtering. So the signal is characterized by rapid fluctuations in amplitude over time, likely due to noise and also interference. And the bottom plot represents filtered radar pulse signal, which is after applying the rectangular windowing filter. So this plot displays the same radar pulse signal but after the rectangular windowing filter process. As you can see, compare both plots. The fluctuations in the bottom plot are reduced compared to the top plot. So the overall process is a rectangular window is applied to the noisy signal. The windowed signal is then passed through a filter which is low pass filter in this case. The main effect of applying a rectangular filter is to reduce the noise in the signal. By multiplying the signal with the rectangular function, the noise outside the window is effectively suppressed. This leads to a cleaner signal with less noise. So as we compare the both plots, we can see that the bottom plot has cleaner signal with less noise after applying the rectangular windowing filter. As we move on to the Hamming window, we have done a simulation for audio signal processing. It simulates a noisy speech signal and applies a Hamming window. Gaussian noise is added to the speech signal to simulate a noisy environment. A Hamming window is generated using the Hamming function in the MATLAB. As we see the simulation results of the noisy speech signal, which is the original signal, that contains both the simulated speech sine wave at 100 Hz and also the added Gaussian noise. The noise introduces random fluctuations in the amplitude, making the speech signal harder to view visually. Below, when we see the filtered signal, the Hamming window smoothens the signal edges and reduces the impact of noise, particularly at the beginning and end of the time domain signal. The amplitude of the signal is attenuated towards the edges because the Hamming window tapers to 0 at the endpoints. This helps in preparing the signal for further frequency domain analysis by minimizing spectral leakage.
I'm going to explain the coding part. The first line is audio read. It helps to read the audio file in m.wav and output the signal as an audio signal and sampling rate as fx. The normalization ensures the audio signal amplitude lies between -1 and 1 by dividing it by its maximum absolute value. This helps avoid clipping when processing or playing back the audio. To design a low pass filter using Hamming window, we have to put the cutoff frequency fx 1 kHz. Signal above this frequency will be attenuated and the filter length, which is 51. This determines the number of coefficient and the complexity of the filter. Longer the filter yield, sharper cutoff but require more computation. Small n represents a symptomatic range centered at 0 to compute the filter coefficient. The h_ideal represents the ideal low pass filter coefficient based on the sin function. The next line represents the Hamming window to reduce spectral leakage and make the filter practical. And then the process will end by normalization, which is ensure the filter as unity gain at DC. So move on the filtered audio line. Filter audio line applies the filter edge to the audio signal to perform convolution effectively, which means removing frequency above the cutoff frequency. And move on to the next part, which is plotting the signal. We basically plot out the signal as per x label time and y label as amplitude, which will display the original and filter out signal for comparison. And the next part is also which is we are not plotting it, but we are giving command to play the audio signal, which will play the audio signal to the computer signals. Computer speakers. Sorry. Next command is to save the filtered audio. Audio write will save the filtered out audio to filtered underscore audio.wab using original sampling rate.
If we run our code, we got the results, the figure 1 and figure 2. The figure 1 is the audio form, which is the first one is original audio form, which represents raw and unfiltered audio waveform. The middle one is filtered audio by rectangular window, also applied by low pass filter. Then third is signal process using low pass filter with the Hamming window. We can see the original audio signal with other signal which is rectangular and Hamming window. Totally different, we can see here. Because the two other signal is filtered by low pass filter using the window, the rectangular window and Hamming window. That's why they are different. But the two filter audio signal seems same in audio form, but we can see the difference at frequency response in figure 2. So in figure 2, we figure out the frequency response. The first one is original audio signal. It displays magnitude spectrum, original signal in decibels, and noise or unwanted components that more ripples you can see higher frequency range, which the filter aim to suppress. The second one is frequency response by rectangular window, which is we see in the figure 1. From the figure 1, we see the frequency response. We can see the difference between the original audio signal between the filter signal. It shows the response from the low pass filter. These side loops are created by Gibbs phenomenon, where the sharp transition in filter we can see here. It also causes oscillation in the frequency domain, affecting the performance. The third one is we can see the frequency response from Hamming window. The main loop is slightly wider than rectangular window. You can see here, better and smoother transition around the cutoff frequency. These side loops are much more smaller compared to the rectangular window, and resulting in attenuation, better stop and attenuation, and reduced leakage. Is more efficient in suppression high frequency noise and artifacts. And the difference between the rectangular window and Hamming window. Hamming window is offer better stop and attenuation by reducing side loops and making it more suitable for application requiring smooth filtering. When we run this code, we play the original audio, then rectangular and Hamming audios. You can see the original audio.
Le jeu n'est point un amusement d'homme riche, il est la ressource d'un désœuvré. Le jeu n'est point un amusement d'homme riche, il est la ressource d'un désœuvré. Le jeu n'est point un amusement d'homme riche, il est la ressource d'un désœuvré.
You can see the original was unfiltered audio waveform and unwanted component may exist. It creates higher frequency range. For rectangular window, the sharp transition in the filter causes oscillation. It makes more sharp and soft. It affects the performance, make the audio suppress very deep and soft. For the Hamming, more efficient suppression and high frequency noise, and more suitable for application requiring smoother filtering. That's all.
Okay, now we see the conclusion. So in the simulation, the audio signal in the time domain after rectangular and Hamming windowing filter are smoother than the original. Then the rectangular window filter's frequency response reveals sharp transitions at the cutoff frequency and ripples in the passband and stopband. After that, Hamming window filter's frequency response has fewer ripples and better attenuation at the stopband. Furthermore, Hamming filtered audio is clear and more natural than the rectangular window filtered audio. Then finally, in audio signal processing, Hamming windowing performs more efficient compared to rectangular windowing. Thank you.